Hello everyone, this is Dr. Gautam Haldar. In this video lecture, we are going to study the following 3 points. The first one is anti-symmetric relation, second one spatial order relation and Poset, and third one is linearly ordered set or chain. And we will give some examples on these 3 points. Okay. So let us start with the first point, anti-symmetric relation. So definition of anti-symmetric relation is a relation, say rho, defined on a non-empty set A is said to be anti-symmetric if wherever A is related to B and B is so related to A implies A is equal to B, where A and B are coming from the set A. If this happens, then we say that the relation rho is anti-symmetric relation on A. Let us take some example of this relation. Suppose our A is equal to say 1, 2, 3, 4. We define a relation rho on A by say 1, 1, 2, 2, 1, 3, 2, 3. So this is a anti-symmetric relation on A. Therefore, rho is anti-symmetric. So the rho is anti-symmetric on A. So these are example of an anti-symmetric relation. Now it is to be noted that symmetric relation and anti-symmetric relation defined on a set non-empty set A are not of negative of each other. Okay, means if a relation defined on a set A is not symmetric, then it doesn't mean that that relation will be anti-symmetric relation and vice versa. We can visualize this concept by taking an example. Suppose our A is equal to say 1, 2, 3, 4. Let our relation rho is equal to say 1, 1, 2, 2, 1, 2. Okay. 2, say 3. Okay. So this clearly this relation is not symmetric relation. This relation is not symmetric relation. If I take one more point here, say 2, 1. Okay. Then we can see that rho is not symmetric because there is a relation between 2 and 3, but for the symmetricness, there should be a relation between 3 and 2, but we see that there is no relation between 3 and 2. Here we see that there is a relation between 2 and 3, but there does not have a relation between 3 and 2. So rho is not symmetric. This implies rho is not symmetric. Also, we see that there is a relation between 1 and 2, and there is a relation between 2 and 1, but 2 is not equal to 1. And therefore this relation is not symmetric, as well as rho is not anti-symmetric. So symmetric and anti-symmetric are not of negative each other. Okay, in the sense of negative each other. Okay. Okay. Now there are lots of examples where we can see that a relation may be both symmetric as well as anti-symmetric. Let us take an example. Suppose our set A is equal to this set, and we are defining a relation rho on A by 1, 1, 2, 2, 3, 3, 3. So clearly rho is symmetric as well as anti-symmetric. Okay, if you closely observe the definition of symmetric and anti-symmetric relation, then we can see that rho is symmetric as well as anti-symmetric. Okay. Okay. Now come to the next point, partial order relation. Partial order relation. A relation rho defined on a non-empty set A is said to be partial relation order relation if rho is reflexive, anti-symmetric and transitive. If a relation defined on the set A is reflexive, anti-symmetric and transitive, then we say that rho is a partial order relation defined on the set A. Defined on the set A. Okay, and the notation of this partial order relation rho is this. We say that the pair A, this partial order relation is called a Poset. It's called a Poset. Okay. Now let us visualize this definition with the help of some example. First example. Suppose X is a non-empty set. Let or A is equal to the power set of X. Now let us define a relation on P of X by, let us define a relation rho on P of X by A is related to B if and only if A is a subset of B, where A and B are coming from the set P of X. Then we see that we show that rho is a partial order relation on P of X. For that we have to prove that rho is reflexive, antisymmetric and transitive. Now in the previous lecture we have seen that this relation rho is reflexive as well as transitive. So in order to prove that rho is a partial order relation, we only just prove that rho is antisymmetric relation. Okay. In the previous lecture we have seen rho is symmetric as well as transitive. Okay. Now for sorry, rho is reflexive and transitive, and here we only prove that rho is antisymmetric. For that, suppose A is related to B and B is rho related to A. So by definition, A is a subset of B. Here B is a subset of A. And these together will imply A is equal to B. Okay. And this implies rho is antisymmetric. Rho is antisymmetric. And therefore rho is a partial order relation. Rho is a partial order relation. And therefore P of X with this rho or P of X with this is a poset. This is a poset. Okay. Now let us take another example. To suppose our A is equal to the set of all real number. Define a relation rho on R by X is related to Y if only X is equal to Y. X, Y are coming from set of all real numbers. Okay. Then clearly here rho is reflexive because we know that X is less than or equal to X for all X belonging to R, and this implies X is related to X for all this. Clearly this, and this implies rho is reflexive. We show that rho is antisymmetric. Suppose X is related to Y and Y is related to X. So from this definition, X less than or equal to Y and Y less than or equal to X, and this implies X is equal to Y. Right? And this implies rho is antisymmetric. Also, you can easily verify that rho is transitive. Verify it. And therefore rho is a partial order relation. Rho is a partial relation, and therefore R with this relation less than or equal to is a poset. This is a poset. Okay. Let us take another example. Suppose our A is equal to the set of all natural numbers. That's it. Okay. Define a relation rho on N by X is related to Y if X divides Y. X divides Y. What is the definition of divisibility on the set of all natural numbers? That we have seen in the previous lecture. You can go through that video lecture. Okay. Now we see that this relation rho is a partial order relation, on n, because x divides x for all x belonging to n, right? We know that. Because x can be written as x into 1, and where 1 is coming from the set of all natural numbers. And therefore, by the definition of division on n, x divides x for all x belongs to n. And this implies x is related to x for all x belonging to n. Suppose x is related to y and y is related to x. And this implies x divides y and y divides x. X divides y means there would exist some natural number, say m, such that y is equal to some m into x. Here also we can get some natural number, say n, such that x can be written as n into y, where n coming from n. If we multiply these two equations, we get xy here. Left hand side we get xy, and the right hand side we get xy into mn, and this implies mn is equal to y, since xy is not equal to 0, right? So we see that m and n are coming from the set of all natural numbers. That means m and n are natural numbers, and the product of two natural numbers is 1, and this implies m is equal to 1 and n is equal to 1, and therefore x is equal to y, and this implies rho is anti-symmetric. Okay, rho is anti-symmetric. Next, we see that rho is transitive also. Verify that rho is transitive, and therefore rho is a partial relation. On set of all natural numbers, and therefore with this relation is a poset. Number 4. Instead of n, if we take the set of all integers, and we define a relation rho in this way, that means x is related to y if and only if x divides y, then this rho is not anti-symmetric. This rho is not anti-symmetric. That we can easily see by taking some example. For example, if we take x is equal to 2, y is equal to minus 2, then there is a relation between 2 and minus 2, and there is also a relation between minus 2 and 2. Okay, because 2 can be written as minus 1 into minus 2, and minus 2 can be written as 2 into 1, right? 2 into minus 1. So there is a relation between 2 and minus 2 as well as minus 2 and 2, but 2 is not equal to minus 2, and therefore rho is not anti-symmetric, and therefore rho is not a partial relation, and so z with this relation is not a poset. It's not a poset. Okay, now come to the next point. Point number 3, linearly ordered set or chain. linearly ordered set or chain. A poset this is called a linearly ordered set or a chain if for all A, B belongs to A, either A is related to B or B is related to A. If this happens, then this poset is called a linear order set or a chain. Okay. Now we have seen 4 examples. Out of 4 examples, the second one, that is, if we take A is equal to say R and we define the relation rho by X is related to Y, if and only if X is less than or equal to Y, then we have seen that this relation is a partial order relation on R, and therefore R with this relation is a poset. And not only that, this poset is actually a linearly ordered set or a chain, because if we take any 2 points from the real number, then that 2 real numbers, between these 2 real numbers, either if we take any 2 real numbers, say X and Y, then either X is less, we know that either X is less than or equal to Y or Y is less than or equal to X. So if we take any 2 real numbers, then this, either this happens or this happens, and therefore this pair is actually a chain. But the first example, we have seen that in the first example we have defined in this way, a relation we have defined in this way. P of X with this is actually a poset, right? Just we have this just we have seen earlier just. But this is not a chain, not a chain. Okay, verify it. I leave it to you to verify. Okay. So let's stop here. Thank you very much.